Okay, welcome everyone. Matt is our speaker today. He's going to be talking about uprolling unrolled quantum groups. Matt, feel free to start whenever you're ready.
Okay, so thank you for the invitation to speak. I'm going to be talking about the content of a paper I wrote with Thomas Kreutzig called Uprolling Unrolled Quantum Groups. And the content of this paper concerns primarily categories of local modules for commutative algebra objects in the category of weight modules for unrolled quantum groups. And so I'll take a few minutes to kind of break down what all of this means. And before I get into some motivations, some results, and then talk about how we can use this to build conjectures for vertex operator algebras. So the unrolled quantum group associated to some simple complex Lie algebra at some complex parameter Q, for us it'll always be a root of unity. You can define it as the smash product of the usual non-restricted specialization with the universal enveloping algebra of the Cartan subalgebra of G. And I'll make this more precise soon. This quantum group was first introduced by Nathan Gear, Bertrand Patiro-Mirand, and Vladimir Turayev for the SL2 case at even root of unity, and they were interested in topological applications. So they showed that the category of modules for this quantum group produces link invariance extending the colored Alexander invariance of Murakami. And I'll kind of touch on soon how actually these applications to quantum topology are a lot stronger than they first appear. Okay, so first, before giving a precise definition of what this quantum group looks like, I'll just fix some notation. So throughout the entire talk, G will be a simple finite dimensional complex Lie algebra, H its Cartan subalgebra, Q its root lattice, and P its weight lattice, with the simple roots denoted in the usual way. Q will be a root of unity of order L, and when L is odd, we'll define R to be L, and when L is even, R is 1/2 M. Then DI, these are the integers symmetrizing the Cartan matrix, so they're just 1/2 the lengths of the simple roots. And RI will be the greatest common divisors of R and DI. This will appear in the definition. And rho is the Weyl vector, as usual. So the unrolled quantum group then, associated to G at the root of unity Q, it's just the C algebra with generators X, H, and K with these relations. And if you're familiar with quantum groups, you may notice that if you just consider the subalgebra generated by the X and K terms, then this is the unrestricted specialization. Or, well, we've taken a quotient of it now. So what this unrolled quantum group is, you just take this unrestricted specialization, you add some generators H with some kind of natural relations. And in our case, we quotient, because it's the quotients that correspond to vertex operator algebras. So we'll call a module for this quantum group a weight module if it decomposes as a direct sum of eigenspaces for the generators HI. And we'll also require that these K generators act as some sort of exponentiation of the H generators as operators on V. So we'll call such modules weight modules, and throughout we'll just be considering this category of modules. And this category is known to be ribbon, non-finite, and non-semi-simple. So I mentioned at the beginning, we'll be looking at categories of local modules for commutative algebra objects in this category. So I'll briefly explain what I mean by that. So a commutative algebra object in a braided tensor category, it's just an object in the category together with a product and a unit morphism. So these have to be morphisms in the category, satisfying the associativity, commutativity, and unit axioms. And rep A will denote the category of objects where V, we have pairs. V is just an object in C, and mu V is a morphism in this category, which turns it into a module in the usual way. So this is very natural. It's just commutative algebras and modules where as objects, they lie in the category, and the product and unit morphisms and the action on the module have to be morphisms in your category. But the category we're most interested in is going to be a subcategory of this category of modules. So this is going to be the subcategory consisting of those modules which kind of don't see, whose action kind of doesn't see the double breaking. And we care about this for two reasons. First of all, the category of local modules is braided. And it also kind of plays an important role in studying vertex algebra extensions. So I'll talk about that soon. So for any algebra object, we have an induction commutative algebra object. We have an induction functor. And so what this functor does is it takes any object in C and sends it to a tensor V, where the action on V, on a tensor V now is just given by the product on A. So you can always construct these modules. And the last thing I need to mention before getting into more motivation and some results is just the notion of the meager center of a category. So if C is braided, then an object is said to be transparent in C if its double braiding with any other object is the identity. And the meager center then is the full subcategory of objects, of transparent objects. And when your category is finite, then triviality of the meager center is equivalent to your usual notions of non-degeneracy, like invertibility of the S matrix. So this should really be thought about as a kind of natural non-degeneracy condition to consider in the non-finite case for non-finite categories. Well, the unrolled quantum groups were initially introduced with some interest in quantum topology, so it's not too surprising that they find more substantial applications to quantum topology. And we'll see that they actually also have connections to vertex operator algebras through their representation theory and through the logarithmic Kasdan-Lustig correspondence. So for quantum topology, these applications come from the fact that their categories of modules are what we call relative modular. Relative modular categories are non-finite, non-semi-simple categories where the non-finiteness and non-semi-simplicity is in some way highly restricted, so we can still work with them nicely. And these categories were modeled after the category of weight modules for unrolled restricted quantum SL2. And they're interesting because they produce topological quantum field theories. And it's now known that for any simple finite dimensional complex of the algebra and odd root of unity, the category of weight modules produces, is relative modular. And there are also some results known for SLMN. On the vertex algebra side, it's expected that the category of finite dimensional weight modules for SL2 at Q, a 2p root of unity, should be ribbon equivalent to the full subcategory of modules for the singlet vertex operator algebra generated by irreducibles. And we don't need to restrict ourselves just to this case if we consider finite length modules over the singlet, then this should be, well, one might guess that it would be equivalent to the category of generalized weight modules for this quantum group. So instead of having the H terms act semi-simply, modules decompose into generalized weight spaces. Okay, so if we have a vertex operator algebra, V, and some category of modules, rep V, which has the structure of a vertex tensor category, then any vertex operator algebra extension of V, which lies in this category, is equivalent to a commutative algebra object in the category with trivial twist and injective union. And further, the category of modules for this vertex operator algebra, which lie in rep V, is equivalent to the category of local modules for this VOA, but now viewed as a commutative algebra object. So this was the second reason I mentioned before for caring about this category. So this gives you some sort of idea. Well, if you have some sort of extension of the singlet, which lies in this category generated by irreducibles, then there should be, if this conjecture is true, then there should be a corresponding algebra object in the category of weight modules whose category of local modules is equivalent to some category of modules over this extension. Okay, and the natural example to consider here is, of course, the triplet vertex operator algebra. So the triplet vertex operator algebra contains the singlet as a sub-VOA. And it turns out that if you assume that the conjecture that there is this ribbon equivalence between the category of weight modules for the unrolled quantum group and the singlet, you can actually construct an algebra object whose category of local modules is in fact equivalent to the category of modules of this triplet. And you can also find the quasi-Hopf algebra, which realizes this category of local modules as its own representation category. And this turns out to be some quasi-Hopf modification of the small quantum group. So this is where the word uprolling in the paper comes from. You start with something like the small quantum group, you introduce these generators H, and then when you look at categories of local modules over commutative algebra objects, well, these are actually representation categories over the small quantum group with some sort of modified quasi-Hopf structure. And I guess I'll mention this algebra object and the associated quasi-Hopf algebra were first introduced by Kreutzig, Ganutinov, and Runkel. And these equivalences were proven in the P=2 case by Kreutzig, Simon Lentner, and myself, and then for arbitrary P by Terry Gannon and Chris Negrin. Okay, so I'm going to start getting into the results of the paper. So let B be a braided tensor category whose objects carry the structure of a vector space and whose invertible objects can be indexed by a lattice script L. And so we'll denote these invertible objects by C sub L. And so an invertible object here just means that it's invertible under the tensor product. So there's some other object such that it's the tensor product of these two is the identity in the category. We associate to this lattice a form for some fixed integer L, and we assume that this form determines the braiding, the action of the braiding in this category on tensor products of invertible objects. Sorry, I switched my language here. Simple currents are the same as invertible objects. And of course, we assume this structure because this is true for the unrolled quantum groups in particular. We don't just want to consider the unrolled quantum groups, we might want to consider, say, the Deligne product of the representation category of unrolled quantum groups with itself or with a category of modules over the Heisenberg VOA. So for any sublattice of this lattice script L, we can associate a object in the category, which is the direct sum of all invertible objects whose index is an L. And then we can classify which of these which of these objects carry the structure of an associative algebra object and a commutative associative algebra object. And I guess I'll also point out that the algebra, which realized an equivalence with the triplet, is of this form in the SL2 case. So for all choices of L, this object can be given the structure of an associative algebra, and it's commutative if and only if this rescaling of L is an even lattice. We don't need to consider just commutative algebra objects. We can consider supercommutative superalgebra objects as well. So if you have some lattice L, you can consider the lattice generated jointly by L and some other entry mu in the lattice, and define the associated object as, again, the direct sum of the invertible objects in this lattice. Okay, then if we've chosen L such that the associated object is commutative, and chosen mu such that mu is not in L, but 2 mu is, then this object, AL mu, is a superalgebra. And it's supercommutative if and only if these two conditions on the form hold. And it turns out that all supercommutative superalgebras, which are direct sums of invertible objects, for which the even component is a commutative algebra object of the kind we've just described, and the odd component is a non-trivial simple object over the even component. All such supercommutative superalgebras have to take this form. So in general, I'll be talking about results on the supercommutative superalgebra objects, and you can just set mu equals 0 to get the results for the commutative algebra objects. So we want to understand the categories of local modules over these algebras. And so, of course, we need to first understand the simple objects. And it turns out that if every indecomposable object in B has a simple subobject, which is certainly true for the category of weight modules, because I should have said the category of finite dimensional weight modules. We assume, so this just holds. Then every simple object in the category of modules over the algebra object is given by the induction functor acting on some simple object in B. So we know exactly what every simple object in this category is. And for the category of local modules, then this will be the induction of simple objects which land in the category of local modules. So our primary example here, of course, is going to be the category of weight modules. And before I proceed, I need to just introduce some more notation. So we'll denote the simple objects in this category by S lambda. And then the invertible objects are going to be the simple objects where lambda, the highest weight of the irreducible module, is in this shift L/2 of the weight lattice of G. And in this case, we'll just use our usual notation for invertible objects. This category also admits projective covers for each irreducible module, which we'll denote by P lambda. Okay, then if we take AL mu here to be a supercommutative superalgebra object in the category of weight modules for the unrolled restricted quantum group, then the distinct irreducible objects, so the isomorphism classes of irreducible objects in the category of local modules, are given by this quotient of lattices. And in particular, this category is finite if and only if the lattice we associated to the algebra object has rank coinciding with that of P. And this lattice is a sublattice of some rescaling of P. So this is really saying the category is finite if and only if the associated lattice has like maximal rank. So if we take the induction of the projective cover of a simple object, and that is the projective cover of the induction of that simple object, and the projective covers lift to the category of local modules if and only if their associated weight is in this rescaling of the dual lattice. We also know that for any object in this category, if its projective cover is denoted by px, then this object induces to the category of local modules if and only if its projective cover does. So we understand well what the irreducible modules are, we understand what the projective covers are, and we understand when any other object induces. It's when its projective cover does. Okay, so we don't want to just understand irreducibles, we want to know a little more about the structure. Is the category ribbon, say, is it non-degenerate? So does it have trivial meager center? So it turns out that the category of local modules is ribbon if and only if this condition on the lattice is satisfied. And if R does not divide 2di for all choices of I, then the category of local modules is has non-trivial meager center if and only if you can find a weight in this set. Remember, this is the set indexing simple modules, just satisfying this condition on the form. So we know what the irreducible modules are, what the projective modules are. We know when this category is ribbon. We know when it's non-degenerate. And now we want to apply this to make some conjectures about the triplet and BP algebras in higher rank. So we do this by identifying some algebra object in the category of weight modules corresponding to these VOAs. Okay, so let L be this rescaling of the root lattice Q by square root R. Then we can define the singlet and triplet vertex operator algebras associated to Q as a kernel of screening operators associated to an intersection of kernels of screening operators that should be associated to each simple root. And so the triplet is just the intersection of the kernels of these screening operators on the lattice VOA, and the singlet is the intersection of the kernels of these screenings on the Heisenberg subalgebra. So clearly the singlet here is a sub-VOA of the triplet, and when you take Q to be just the root lattice of SL2, then this recovers the usual definition for the singlet and triplet VOA. So we want to identify some algebra object in the category of weight modules corresponding to the triplet. Well, if there is such a ribbon of equivalence, then it in particular must preserve twists. So we can decompose the triplet as a module of the singlet and compare the action of the twist in the category of weight modules for the quantum group with the action of the twist we would expect for the singlet. So this would be the twist you would get coming from a vertex tensor category structure, which we would expect to exist. And if you do this, you find that the associated algebra object should be the algebra object associated to the lattice RQ. And this is when Q is, again, associated to SL2. This is now the algebra object which realizes the equivalence which is known to hold for the SL2 triplet. Okay, so we fixed our algebra object and we know how to determine its structure. So now we just apply our previous results to this example. So if you do this, you find that the irreducibles are going to be the induction of simple objects indexed by the quotient of the weight lattice by r times the root lattice. And you can show that this quotient has det A times r to the rank of G elements, where A is the Cartan matrix of G. So this gives us a prediction for the number of isomorphism classes of simple modules for the triplet in higher rank. We have our condition for when this category is ribbon, and it's easy to see that this just always holds because the Weyl vector is in the weight lattice. And we can check directly using an argument on weights that this category has trivial Muger center. So you need to check that the condition I stated before in the previous proposition does in fact hold for this example. And you can check this, and it does. So this leads us to a conjecture for the higher rank triplet algebra. And this conjecture is that the category of modules is finite, non-degenerate, and ribbon. And the number of isomorphism classes is precisely the determinant of the Cartan matrix of G times r to the rank. Okay, and so now we want to do the same thing for the BP algebras. So the higher rank BP algebras, which we denote BQR, let dr be the diagonal isotropic sublattice of these rescalings of the direct sum of these rescalings of the weight lattice, and define WR to be the tensor product of the lattice VOA, associated lattice VOA, and the Heisenberg VOA of the same rank. Then the higher rank triplet is defined again as a kernel of screenings on this vertex algebra. And we can decompose, we can show that this VOA is a module over the tensor product of the singlet with the Heisenberg. And we can decompose it as a module and compare twists again, and we find the corresponding algebra object. But this time the algebra object is not in the category of weight modules, it's in the Deligne product of the category of weight modules with some representation category of the Heisenberg VOA. So this was one of the reasons why we didn't want to just take our initial results and state them in the category of weight modules. We wanted to kind of state them more abstractly so we can apply it to this category as well. And here, A sub r is just the square root of -1 over r. So now we perform the same analysis we did for the triplet. And if you do, you find that this category is ribbon if and only if some condition holds. So then we need to check when this condition holds. It doesn't always hold. So this is for all lambda in the weight lattice. Well, the Weyl vector is in half the root lattice, so you know that this holds if the Weyl vector happens to be in the root lattice or if r is odd. We can perform a similar computation on weights to determine which irreducible modules induce to the category of local modules. Sorry, the first point should say that the category of local modules of this algebra object is ribbon, if and only if this condition holds. And you can check directly by computation on weights again that this category does in fact have trivial Muger center. So the conjecture we'd construct here is that the category of modules over this VOA has trivial Muger center. It's ribbon if r is odd, or if the whale vector is in Q. So this kind of coincides with the SL2 case where you have ribbon only if R is on. And we can index the irreducible modules in the way I've written here. So this indexing comes from the fact that not all irreducible modules in the Stellene product are going to lift to the category of local modules. And then we pick up some relations which come from the fact that some of these modules induce to isomorphic modules. They become isomorphic after induction. Okay, so this is our conjecture for BQR. So we've kind of what we've really done here is we've constructed large families of categories. We know when these categories are ribbon, we know when they're finite, we know when they're non-degenerate, and we've made some predictions about associated VOAs. So I'd like to finish off here by talking about some potential future research directions that I think are especially interesting. So in the SL2 case, it wasn't just the algebra object that was constructed. It was Kreutzig, Ganutinov, and Runkel who constructed a quasi-Hopf algebra, which is actually equivalent, has representation theory equivalent to this category of local modules, and therefore equivalent to the triplet algebra. And so for each one of these algebras, we can ask, well, can we write down the quasi-Hopf algebra, which has representation theory equivalent to the category of local modules for this supercommutative superalgebra object? And this should be possible, at least for abelian equivalences. And I would expect that these quasi-Hopf algebras will be quasi-Hopf modifications of subquotients of the unrestricted quantum group. And in particular, if you take the lattice to be kind of maximally large or maximal rank, then you should just get back the small quantum group, or a quasi-Hopf modification of it. So I mentioned before that these categories of modules, the category of weight modules is relative modular. So it has applications in quantum topology through the construction of TQFTs. Well, then of course we could ask, do any of these categories of local modules have similar applications? So do they have a relative modular structure or a relative spherical structure? So relative spherical is a slightly simpler formulation that produces three manifold invariants. Of course, we could ask if we can find and study more sophisticated examples of algebra objects. So these algebra objects were all direct sums of invertible objects or simple currents. So the VOAs they would correspond to, if they do correspond to one, would have to be simple current extensions of the singlet or singlet times Heisenberg. And of course, you might want to look at more sophisticated extensions. And finally, even if we can't prove a ribbon equivalence in beyond rank 1, this is likely inaccessible for some time, we can ask how much can we show? So can we show an abelian equivalence? Can we compare some character formula? If there's something like this we can do for the easiest example. So the first example you might consider is then the BP algebra at p equals 2 associated to SL3. And in fact, this algebra is isomorphic to affine SL3 at level -3/2. So this is quite an interesting example. Okay, so that concludes my talk.
Thank you so much, Matt. Let me stop the recording.